Hello, this is Module 5, Lesson 3, which is soil. So basically, during the notes, I want you to think about how does eroded rock become soil? So that's kind of the focus of these notes. All right, so just a review for the vocabulary. An organism is something that is alive or maybe used to live, but it has all the characteristics of life, so basically living. All right, so when we talk about soil, soil is formed from eroded rock, and it's basically just the top layer of crust, very, very thin. And it's where the nutrients are held, it's where decaying matter is held, it's where all plant growth occurs, where the roots are bound. So that would be soil. And then if we look at how soil develops over time, it goes through a process of steps. So basically, if we look at the first part, it's disintegrating rock. So we start with bedrock. And then there's organic matter laid on top. So that would be any kind of decayed plant, animal, things like that. And it breaks down. So we've got weathering occurring. And this could be chemical or physical, which is mechanical weathering. And so over time, that breaks down and mixed with that organic material breaks down and forms this, what we call A horizon. So it's a type of soil. And then it later forms B horizon. And then you've got the parent material down below. So notice how the bedrock stayed down below the whole time. And basically, we just kind of weathered this top layer and built up organic material, clays from the rock, and now that supports life. Whereas before, when it was just the rock itself, it didn't support much life at all. So that's how it develops over time, and this could take thousands and thousands of years. So it takes a really, really long time. All right, so if we look at the soil development in more detail, so we've got this layer that's formed up here. So this would be our A horizon. And then you've got little things burrowing into it. You've got the roots, you've got worms, a little mouse, all kinds of things. And those help to aerate it. So they help to allow water to pass through, but it also allows there to be air and further breakdown of nutrients and rock material to form more and more soil. So those things are actually really, really important, that that aeration or buildup, so that it allows the water to filtrate through and nutrients and all kinds of things. So very, very important. All right, and then our layers that we have. It's a little bit hard to see on this picture. It's a little bit blurry, but we'll go over it in detail in just a minute. So basically, you can see different layers. The R, which is at the bottom. So this right here, this would be our residual rock, our bedrock. And then above that, we've got O horizon, which is on the very top. That would be our organic material. And then we've got A, B, and C layers. And so A is our really good soil that we generally know as like black, rich soil. B is a little bit lighter in color. A lot of times that would be our clays. And then C is really undeveloped rock material. So around here, we have a lot of B and C. Unless you live by the river, we really don't have a lot of O or A horizon soil. All right, so this original soil is called R, or residual soil, basically. So you can see in this picture, this is the original bedrock. And then the rock that's breaking down when that soil is first forming, anything above that that has broken down from this original material is called residual soil. So it resides where it was formed. So basically, like you living at home with your parents, you would be residual kids. So you live where you were born or formed or whatever. But this would be our residual. And then transport just means it's transported somewhere else. So if we were to take this layer of soil that's shown here above this blue dashed line, and we were to move it somewhere, like by mass movement, like let's say erosion, a landslide, something like that, wherever it moves to, that would be our transported soil. So it's transported to somewhere else. So residual is, it's where it formed, it's bedrock, parent rock is below, whereas transported, it has moved to somewhere else. All right, so here's a more detail of the soil profile that I was talking about. So on the right, the picture you guys can see, we've got a really nice organic layer, A layer on top. That's our dark soil here. And then you can see the different layers down below. So we've got B down here. We've got a little bit of C. There's no bedrock. Bedrock would be below this picture. And then on the left, we see the different horizons. So you've got your surface layer, which is your organic material where the grass is. And then down below that, you've got topsoil. And then you've got subsoil, parent material, and you can see those are labeled. So O is on the top, and then you've got A, B, C, and then R would be the bedrock. So that's the original parent material of that soil. So here we can see really, really nice distinctive layers. This is very common in the Midwest. So we can see these layers here. We've got our organic material, our A horizon, B, C, and then our R horizon, which is our original bedrock. So very, very distinct profile. And you guys have probably seen like around town as you're driving or just looking around, anywhere where the hill is exposed, you can see those different layers. We do not have these nice layers. We mostly have this. So like I said, unless you live by the river and there's lots of organic material, then you probably do not have this. You probably just have this, especially if you live on any of the hills or any of the areas around Shasta High School. All right, so here is a more detailed analysis or description of those layers. So you've got the O horizon, which is the organic material, A horizon, which is the weathered rock, and it's really good soil. So it's really mixed with a lot of nutrients and organic material. B is that redder layer that I was talking about. We've got some of that clay type material. C is the rocks. So if you've ever tried to dig a hole around here, you hit that C layer pretty fast. And then the R, which is basically the bedrock. And so that would be down below these layers here. All right, and then once again, here is our distinct layers. And then it also adds in a couple terms on the left, alluvial and illuvial. And so alluvial is where you've got water filtrating through. You've got nutrients. Illuvial, that is where you hit the clay layer, and that is basically water is not filtrating through. So the nutrients stay in this zone right here. Same with runoff, or same with anything like that you might be, I guess my battery's low. So anything that might be moving down through the soil, this would be our area where it goes down through like nutrients. And then here it doesn't. So here is basically our clay layer. All right, so things that factor into soil formation, we have 5 things basically. So climate, topography, parent material, biological activity, and time. And we'll talk about each of these here. So all of those combine to form the types of soil. So some places we have really good, rich soil, like in the Midwest. Some places we don't because there hasn't been enough time, like out here in California, not in the valley, but in Redding area. So it really varies by region. It also varies by how much rainfall there is, how much vegetation there is, how much plant and animal material. So there's huge factors that factor into whether the soil is going to be rich or not. So climate is the first one. Climate is probably the most significant in the fact that if it's a desert, then you're not going to get much organic material. And if you don't have much organic material, then you don't have a lot of things breaking down to form soil. So you need that. If you have a really wet environment, like let's say in Oregon or Washington, then you're going to, as long as you have plant material, which you should, you're going to have a lot of organic material, and you're going to have really rich soil. So that climate plays a big factor in the types of vegetation, which plays a big factor in the types of nutrients that are added to the soil. All right, topography. If you have big mountains and cliffs, then you're going to have much more poor soil than if you have like a valley, for example. And then also, this talks about different slopes. So in the northern hemisphere, if you have a south-facing slope, it receives more sunlight, so more vegetation can grow. Whereas if you have a northern-facing slope, there's not as much sunshine, so you don't get as much growth. So that definitely makes a big difference. And think about the last time you went hiking on any of the hills around here. There's definite difference in one side of the mountain versus the other, and that's because of rainfall. It's because of sunlight. So that does play a big factor in the types of vegetation. And then also, what types of vegetation? So oak trees make pretty poor soil. They have real acidic leaves, and so the soil is not very rich. Whereas if you have more deciduous type trees, maple trees, that kind of stuff, then you'll have better soil. And then also vegetation helps to hold the soil. So if you don't have a lot of vegetation, then what's going to happen when it rains is that soil is just going to run down the hill, and any soil that has formed, and you're just going to be right back to the bedrock material or the sea layer material. So you really have to have vegetation holding the soil in place. That's kind of why after the Carr fire, they put a lot of sandbags and hay rolls and things like that down to help minimize erosion, because there was no plants to hold the soil anymore. All right, and then parent material, like I said, the parent material, whatever is there, is going to make a big difference in what kind of soil is formed. So, like out here, for example, in California, we have a lot of clay. We have a lot of iron in our rock, and so that forms really clayey type soil. Whereas in the Midwest, there's a lot of sedimentary rock, and so that forms really nice sandy, loamy soil, which is really good for growing things. So whatever is breaking down underneath, like in this picture, that is going to be, if this is residual soil, this is going to be the soil is forming from this. So if this is a poor material to start with, then the soil is going to be a pretty poor soil. All right, and then animals and plants, I said, were really important. So whatever is breaking down, like for example, these mushrooms is fungus. They are decomposers, and they're breaking down organic material into nutrients that the plants can use. The worms are breaking down soil by aerating it, moving it around, creating spaces for water and nutrients to go in. So the types of organisms you have play a big role. So that's why in a desert, you're not going to have very good soil. One, you don't have the climate for it. So you're not going to have organic material, but then you're also not going to have the organisms either to help move that around. All right, and then time. So I said to fully form soil is thousands and thousands of years to fully form soil. So it takes a really long time. And so California, in geological speaking terms, is very new compared to areas in the Midwest, for example, that have been around a lot longer than California has. So California has added land. I had mentioned before that Redding used to be on the shore of the ocean. So all of the land basically west of the Rockies is fairly new geologically speaking. So it hasn't taken thousands of years to form. The Midwest has formed a lot longer. So given time, the soil will get better and better in California. All right, and then we've got these different types of soil. So the soil orders, we've got intosol, malsol, and ultisol. And so some examples of where those are located. So California has intosol, which is very immature soil. So like I mentioned, it doesn't have a lot of time to form because California is fairly new to North America. And so that, for thousands of years, California will have better soil than it does now. And then Mollisol, Kansas is a great example of this. This is very rich, very thick A horizon. A horizon is the topsoil, the stuff that you would buy if you were to buy like potting soil at the store. And so this is very rich in nutrients, very good soil. And then Ultisol, Florida has an example of this. It's highly weathered, very thin A layer. So this is very, very old soil. Been around for a very long time. So you can see eventually California, given time, will have more of a mollisol, and then given time, even more time, would have more of an ultisol. So it's just depending on time as far as what types of soil and what kind of layers they look like. All right, so here's some examples of what those look like. So intosol, California, very typical. Very few, you can see this is some maybe sage, lavender, basically just clay. So this is very typical, especially of Redding area, very typical. This is the Midwest, so Mollisol, we've got very distinct A horizon. This is the B horizon. C would be below it. And this is basically just C. This is the C horizon. You don't even see it in this picture. And then Oldesol, this is very old. So we've got this C layer. We've got a almost non-existent B layer, and then a very, very thin A layer. And that's just because this soil is very, very old. All right, so this is a soil classification based on texture. So we're going to practice using this in class. But the way you would read it is you've got this triangle, and it looks more complicated than it actually is. But we've got clay on this side, and this is percent. We've got percent silt, and we've got percent sand. So if I have a loam soil, so let's say, and clay loam is probably the best soil, so let's say clay loam. So I've got a clay loam. So if I want to know right here, percent of everything, so it's 70, it is 35% sand. So see how I'm reading these? They are sideways. They are read like this. So 30% reads along this line here. 50% reads along this line here. And then if I'm reading clay, I read across. So these are, horizontal. So 50% is this, 60% is this, 70%. And then over here, percent silt. So I'm reading down this direction. So 20% here, 10%. So back to that clay loam. So right here, this would be 35% clay. This would be 30% silt. And this would also be 40% sand or something along those lines. So it should equal 100 as you go through this. And I will show you, we'll practice in class how to use this. But it's just a soil texture triangle. And it basically determines the type of soil that you would have. So you would look at your soil and you would determine approximately how much clay, silt, and sand you see in your soil. And that would tell you what kind of soil you have. In California, in Redding, it's mostly this. So we have clay here in California. I said that this type of soil right here is some of the best, most fertile. And that's just kind of a healthy mixture of clay, silt, and sand. All right, so the fertility has to do with these things. So topography. So is the sediment and erosion going to settle into the valleys? Like, for example, the Sacramento Valley. All of the rivers and everything carry that fertile eroded material into the valley. And so the valley tends to be a lot more fertile. Along the rivers tends to be a lot more fertile than it is on the hillside. And then how much mineral and nutrients are there? How much organic material is there? How many microorganisms are present? How much precipitation? Is it going to rain a lot? Is it not going to rain a lot? And then the acidity level. So I mentioned that the oak trees, they have really acidic leaves. And so those don't make very good soil because they're too acidic and they really don't allow other things to grow. All right, and then we get to soil color. So soil color is also very important. You've seen that our soil is very red. It has a lot of iron in it. So what they do is they use this pigmenting. So these are the pigments of the soil. And you can see that this is very good, very rich soil. And then if you've got a lot of gypsum, it's going to be very light color. Calcite is a light color, dolomite. These are all things that we see in our soil. And so it just depends on, once again, like the parent rock, what is breaking down to form that soil. So if we've got a lot of quartz breaking down, then you're going to have a grayish color. If you've got a lot of gypsum, it's going to be a lightish color, and so on. So they use that to kind of figure out what type of soil and how fertile it is, what kind of nutrients are in there, because nutrients are important for plant growth.
formation of soil has taken millions of years, but for us to truly understand it, we must first look to its origins and find out exactly how it was formed. Fundamentally, soil is derived from bedrock, and it's the weathering and eroding of this bedrock that starts the process of soil formation. Over time, bare rock like these are exposed to the elements, with weather like wind and rain, heat and freeze-thawing helping to break up the surface of the bedrock, fracturing it into many smaller pieces. Eventually, these pieces are broken up further and form the physical component of soil. As you might imagine, almost nothing could grow on a pile of fractured rock like this. There are minerals present in the rock, but they're unavailable for the plants. And there's almost nothing to hold water, which is essential for life. This is where microscopic life comes in. Microbes and algae are able to utilize the minerals held in the rocks and start to grow in the little nooks and crevices. Most importantly, these tiny organisms fix nitrogen and carbon dioxide from the atmosphere, leading to a buildup in organic material. And this process paves the way for another key group of organisms that are instrumental in the process of soil formation. These are the lichens. Lichen gets most of what it needs to survive from the atmosphere, hence its remarkable ability to survive in extreme locations. Lichen is formed from an incredible symbiotic relationship between algae and fungi, and it's these bizarre organisms that would have been the first to take advantage of the organic material left over by the microbes and algae. Not only can lichen survive without soil, but through the secretion of acid, it also chemically erodes the rock that it grows on, which frees up a wealth of beneficial nutrients. When the lichen dies, a small deposit of organic matter is left and gets trapped inside crevices within the rock. As more and more lichen grows and dies, this layer of organic matter, rich in nitrogen and essential minerals, builds up, allowing rooting plants a foothold in an otherwise inhospitable environment. This process is long and slow, typically taking 500 years for just 1 centimetre of topsoil to form. This old quarry is a great place to see soil formation in action, as it mimics the natural evolution of soil. Originally, there would have been a lot of bare rock like this, but over time, as the organic matter built up and up, it's led to the succession of larger and larger plants. As these die, they feed into the formation of more soil and allow a diverse range of plants to grow. Erosion is a huge issue in Britain. Since 1850, we've lost 84% of our fertile topsoil, at a rate of around 2 centimetres a year. Soil degradation through current farming practices is currently costing our economy $1.2 billion a year, and there is a real danger of significant reductions in our farming yields in the coming decades if nothing is changed. These figures portray a rather gloomy picture of our soil situation. However, all is not lost. By truly understanding how soil interconnects with both the physical and biological worlds, we can start to work with the soil in harmony and manage it responsibly for both wildlife and future generations.